All right, welcome. In this video, we're going to talk through some electrolytic cells practice. And there's three questions here. And for these three questions, all the information you need is in these standard reduction potentials here in this table. So we got our table of standard reduction potentials and the voltages. And then again, just as a quick refresher here, we know this relationship, delta G is negative NFE. So the larger, like the more positive the voltage, the more favorable the reaction is. So this is how we're going to figure out which reaction is going to occur. The one with the larger voltage is going to be the most favorable reaction. So that's kind of our thought process we're going to apply here. So these are going to be examples of electrolytic cells where we have some aqueous ionic solutions. So this example, we've got some nickel bromide in a solution. So if you imagine what you have, it's electrolytic cell. So we have some sort of power source. We've got a wire. We've got your two electrodes. They maybe are made of some substance like platinum, or who knows what the electrodes are made of. They just seem to be something that conducts electrons through the surface. And these electrodes are placed in a solution of nickel bromide. So nickel bromide is an ionic compound. So when it dissolves in water, it's going to make nickel ions, bromide ions, and it's dissolved in water. So these are the three things that are in the solution: nickel ions, bromide ions, and water. So one of these three substances is going to be reduced at the cathode. So let's label this one the cathode. That's where the reduction is going to occur. And then at the anode, one of these three substances is going to be oxidized. So let's figure out what our possibilities are. So first, let's take a look at who is most likely to be reduced. So again, we've got three substances in our solution: nickel ions, bromide ions, water. And let's look and see as who has the largest reduction potential. So here's nickel ions being reduced. That's got a negative 0.25 volts. And then here is water being reduced, and that's negative 0.83 volts. And if I'm looking for a reaction that shows bromine being reduced, there actually is no, let me rephrase this. There is a reaction that's showing bromine being reduced, but we don't have liquid bromine in our solution. So we don't have any Br2 present. What we have is Br minus ions. And if we look through our reactions, we don't see any that have Br minus gaining more electrons, okay? The bromide ion, it's already negative. It's not likely to gain another electron. So notice how that's not even a possibility. So that's why I kind of crossed bromide off our list. So our anions are already negative. They are not going to gain another electron. So our anion cannot be any further reduced. So we're trying to figure out who's going to be reduced. We're comparing the nickel ion, which is the cation, and water. And if we compare these two, it looks like the nickel ion has a larger voltage. So negative 0.2 is greater than negative 0.8. So my nickel is going to be reduced. So that's going to be the reduction half reaction. So now let's look at our oxidation. So again, we've got three species that could possibly be oxidized. So we've got nickel ions, bromide, and water. So to get the oxidation, what we have to do is we have to take these reactions here and flip them around. So let's, I'm going to erase these ones right here. And we want a reaction that once we flip it around, it will show, nickel, bromide, or water being oxidized. So this reaction, when I flip it around, it's going to show the bromide ion losing electrons. Okay. And then for water, if I take this reaction and flip it around, it's going to show water losing electrons. So when I'm looking for the oxidation, I want to be looking at kind of like the right-hand side of the arrow, because when I flip this around, what's on the right becomes the, reactants. Okay. So, and notice that if I look through these possibilities, the nickel +2 ion does not show up on the right for any of these ones. So the nickel +2 ion is not, there's no oxidation possibility. So the only two things that could possibly be oxidized are my anion and water. So here are these two possible oxidations. So I flip both these reactions around, if you can see where I got this from this sheet up here. And when you flip it around, it changes the sign of the voltage. And then whichever of these reactions has a larger voltage is going to be more favorable. So these two possibilities, after I flip them around, it looks like the bromide ions, that is the most favorable oxidation. So that's going to be, that's the reaction that's going to occur at the anode. And so if we add these up, so if we can draw out kind of what's happening here in the cell, over here at the anode, you've got your bromide ions are turning into liquid bromine, and they're giving up electrons, okay? And these electrons are going to travel through the wire over here to the cathode, and over here at the cathode, the nickel ions are going to grab those electrons and form solid nickel. So we would see a buildup of solid nickel over here on this on the cathode as we're forming these solid nickel, and then over on this side we'd notice some liquid bromine being formed. Okay, and if we add these up, we can get the overall reaction. Remember, with the overall reaction, we should notice that electrons gained should equal electrons lost, so they should cancel out when you add up these two reactions. And then to get the overall voltage, I'm just going to add these up the way they were written. Okay, so yeah, because notice how I already like flipped this reaction around. So I flipped the reaction, turned it into an oxidation. So there we go. So there's my overall voltage, and I can convert my voltage into a delta G value by plugging it into this equation. So delta G equals negative NFE. So N is the number of moles of electrons that are transferred. So in this case, it's 2 moles electrons. F is Faraday's constant, you find on your equation sheet. And then your voltage, we just figured out earlier in the problem. And if you look on your equation sheet, it tells you a volt is a joule per coulomb. So that kind of helps us figure out what the units are here. So 1.32 volts, that's 1.32 joules per coulomb. And then we should notice that moles, electrons cancel out, coulombs cancels out. So your answer is going to be in joules. And we should notice that your answer is going to be positive, because notice how we had negative voltage and negative times a negative. It's going to be positive. So that's because this is an unfavorable reaction. So this is a reaction that will not go unless we hook it up to a power source and kind of force this reaction to go. All right, let's look at another example. Let's look at water being electrolyzed. Okay, so notice how they only mention water. They say there's some other electrolyte in the water, but it's not going to react, so we're going to ignore it. We're just going to focus on the water. So we know that water is going to be oxidized. So we're looking for a reaction that has water losing electrons. And we also know that some water is going to be reduced. So again, because if the only thing you have present in your solution is water, then water must be the thing being oxidized and the thing being reduced. So, and notice like the way I kind of wrote down the backbone of this reaction. If something is oxidized, that means it's giving up electrons. So the electrons are going to show up on the opposite side of the arrow. If something's being reduced, that means it's taking in electrons. So the electrons would show up on the same side of the arrow as that substance. So that's another trick to kind of help you remember the difference between your oxidation and reduction reactions. So let's look at this second one first. So I see a reaction right here that looks like I have water gaining electrons. Okay, so it looks like for every 2 waters, I grab 2 electrons and I form a hydrogen gas and 2 hydroxides. Okay, and then I'll write down the voltage. It looks like it's negative 0.83 volts for this one. And now I want to look for a reaction that has water giving up electrons. So the electrons are on the opposite side of the arrow. And that looks like this reaction right here. Do you see how this one, the water is on one side and electrons are on the other side? So if I were to flip this reaction around, so my products here, 2 waters, that becomes my reactants. And then my reactants over here, my oxygen gas, so O2, and then hydrogen ions and 4 electrons. So the reactants in this reaction, to flip them around, they become the products. Okay, and when I flip this reaction around, remember the sign changes. So now this is negative 1.23 volts. And then I want to add these 2 reactions up to figure out what the overall reaction that's occurring in the cell. And the key thing with this kind of problem is you got to remember that electrons gained need to equal electrons lost. Right now, I am gaining 2 electrons, but I am losing 4 electrons. So I need to double everything in this bottom reaction so that electrons gained equals electrons lost. So let's go through and double everything. So the 2 becomes a 4. This right here becomes 4 electrons. This becomes a 2. And this over here becomes a 4. All right, so now I'm going to add them up. And I should always notice again, electrons should cancel out. So I have the same number of electrons on the left and the right. And then I've got 2 waters plus 4 waters on the left. I'm going to simplify that in a moment. And then on the right, I've got oxygen gas, and I've got 2 hydrogen gas, and then I've got 4 hydrogens and 4 hydroxides. So what you might remember from acid-base chemistry is when the hydrogen and hydroxides come together, they form water. So these 4 hydrogens and 4 hydroxides, they're going to get together and form 4 waters. And then notice, oh wait, I've got 4 waters over here and 4 waters over here, so those end up canceling out. So the reaction that we're left with is just 2 waters form an oxygen gas and 2 hydrogen gas. So that is our balanced equation for that overall reaction. So this is the electrolysis of water. We're basically just breaking it down into its elements there, oxygen and hydrogen gas. And predict the sign of E and G. Well, we know that when it's electrolysis, that this reaction is unfavorable. This is not something that occurs on its own. Like if you have a glass of water, it's not going to spontaneously start bubbling and forming oxygen and hydrogen gases. We need to hook this sample up to a power source in order to force this reaction to run. So since this reaction is unfavorable, that means the delta G is positive, and that means the E is going to be negative. Because again, remember this relationship between G and E here. So there we go. And then we can actually calculate the values of E and G. So since we already have these reactions written out in the correct way, to get the overall cell potential, I can just add together my oxidation and reduction. So they're both negative. Remember, this is an unfavorable reaction there. And so we're just going to add those up, 1.23 plus 0.83, and you get, just checking my mental math here, negative 2.06 volts here. So that's the way I like to do this type of problem is I flip the reduction and turn it to an oxidation. That changes the sign, and then I add them together. I do want to point out, if you look in the textbook and on some of the answer keys, they show a different way, which gives you the same answer, but they write it this way, that you take the reduction at the cathode and subtract the reduction potential from the anode. So basically what that means is you take your reduction, which is negative 0.83, and you subtract the 1.23. Notice how we get the same answer. It's just a different way of thinking of it. So this way thinks of it as a subtraction. This method thinks of it as like you're flipping it around and then adding it. But it's the same thing method. You know, either method works there. Okay, so we know the value of E, and then we should be able to find the value of delta G. So delta G is negative NFE. So the negative, and then the N is, we got 4 moles of electrons. So it's how much is being transferred. So it's basically what's the coefficient in front of the electrons in this balanced overall reaction here. And then F is Faraday's constant, which now I'm blanking. Yeah, 96. It's on your equation sheet. You don't have to memorize it. So it's 96,485 coulombs per mole electron. So notice how moles electrons cancels. And then our volts is negative 2.06, but a volt is also a joule per coulomb. Again, it shows you this on your equation sheet. You don't have to memorize it. So coulombs cancel out, and so you're going to go through, you're going to have a negative times a negative, so your answer should be positive, and then you are going to report it in joules. And if you want to, you could then convert your joules into kilojoules, since the question did not specify what units your answer had to be in. But just make sure you do label your answer with units. All right. So those are two problems there. Should we do one more? Sure, let's do the last one. So we've got one more example of electrolytic cell. This time your cell contains, sometimes I find it helpful to draw this out, it contains manganese ions, an iodide, and water. So it's an aqueous solution of manganese iodide. And again, we're going to hook up some electrodes here, connect it to a power source. Okay. We're going to force an oxidation reduction reaction to occur. So if I'm trying to figure out who is being, let's first look at who is being reduced. So the substances that are likely to be reduced, remember reducing means gaining electrons. So it's either going to be our cation or water. Anions are already negative, so they're not going to be reduced. They're not going to want to take more electrons. So for your reduction, it's either going to be the cation or it's going to be water. So let's look at our cation in this case. It's manganese is our cation. And if you look over here at your reduction potentials, I don't need to rewrite it yet. So this is the reduction potential for manganese. So it's a negative 1.18. And then our water, the water's reduction potential is negative 0.83. So in this case, it looks as though water is actually better at being reduced than this cation is. So who's going to be reduced? It's water. So here is the reduction that is going to happen over there at the cathode. So we're going to form some hydrogen gas over there. The voltage is negative 0.83. Okay, now let's look at the oxidation. So who is likely to lose electrons? Remember, oxidation means losing electrons. It's either your anion or water. So your cation is already positive. So your cation is not going to lose any extra electrons, just like your anion is not going to gain any extra electrons, since they're already of that charge. Okay, so now let's look at our anion. Our anion is iodine. So I'm looking for a reaction in which iodine is oxidized. So I'll use a different color pen here. So here's our iodine. Whoops, this reaction right here. Well, we can't see the whole thing, but it looks like when you flip this around, it's two iodide ions turn into I2 solid, and they generate 2 electrons. And when we flip this reaction around, it flips the sign. So this reaction has the oxidation potential is negative 0.53. So I flip it around to become an oxidation, I flip the sign. All right, my other possibility is water. Water could also be oxidized. So here's the reaction that shows the oxidation of water. So when I flip that around, my reactants are 2 water molecules, and my products are oxygen gas, 4 hydrogens, and 4 electrons. And this one, when I flip the sign, it has an oxidation potential of negative 1.23. So here's my 2 possible oxidations. And remember, the one that has the larger voltage is more favorable. So in this case, this top reaction is the more favorable of the 2. So it looks like what's going to happen in my electrolytic cell here is over here at the, let's call this one the cathode. There's a reduction reaction that's going to happen. This is going to be the reduction of water. So what we would observe happening is we would see some bubbles because we are forming hydrogen gas. And we're also forming hydroxide ions. So if this solution had a pH indicator in it, we might notice a color change happening over here at this at the cathode because we're forming hydroxide ions. So the solution over here is becoming basic. Over here on this side, at the anode, the oxidation is occurring, and who's being oxidized is my iodide. So what we would observe over on this side is we would observe some solid iodine being formed. So you maybe get a layer of iodine on your anode. And then what are the manganese ions doing? They're not doing anything. So they're just hanging out. They're not being oxidized or reduced. They're just hanging out in solution. So to write the overall reaction, I would add up these 2 half reactions that are happening here. So I end up with 2 iodide ions and 2 waters and 2 electrons on the left. And then I have a solid iodine and 2 electrons and hydrogen gas and 2 hydroxides over there on the right. My electrons cancel out, and then I'm left with my overall reaction here. The cathode, what's happening at the cathode is the reduction of water. We already discussed that to the side, but I'm just going to rewrite it there. And then the sign of E and delta G, so it's an unfavorable reaction, so it's got a positive delta G and a negative E because it is unfavorable. And to find the values of them, I'm going to add up the voltages here. So let me rewrite this real quick so we can see where we're getting these numbers from. So the oxidation was negative 0.3 volts, and then the reduction here, here's our reduction, was negative 0.83 volts. So we're going to add together our oxidation and reduction. It gives us negative 1.36 volts, I believe. And then your delta G, negative NFE. Again, you're going to, don't forget the negative out front. And then N is the number of moles electrons, which is 2 in this case. So we're kind of gaining, and there we go, we're gaining, losing 2. F is Faraday's constant, so 96,485 coulombs per mole electron. And then our last value of the voltage is negative 1.36 volts, which is a joule per coulomb. So there you go. You can stop and solve. You'll end up with a positive value that is in joules. And hope this helps. Let me know what follow-up questions you have.